Just a quick little review from last time. Last week we talked about air pressure, just pressure. And in our class in GChem, we're actually, we do the boring stuff with the math and all of that. And we'll do some fun things in here. And one of the things we talked about was that the air weighs 15 pounds, so I got a 15-pound weight per square inch. And we can imagine that this is all the different types of air. It would look like this weight. And I have marked off in an unscientific way, I just put some tape on there, in a rough approximation to the amount of oxygen that takes up the weight of the air. And it's around 21%. And we're going to talk about that 21% today. What if it was more? What if it was less? That's what we're going to think about. What are the implications of that? When I give this talk to churches and different places, it always leads into this conversation right here. And it probably could be its own talk at some point. Biologists and archaeologists, who studies dead animals and pulls them out of the ground? They see fossil structures. Paleontologists, right? Paleontologists. They got so many ologists there. We just have chemists and biochemists. And they got a lot of ologists. So when the ologists are studying the different creatures that have lived long ago, because we find them very deep, they find monsters, huge animals that have lived in the past. And because of that, there is a hypothesis that our air once had lots of oxygen in it, because that could support very large creatures. And in fact, I was just in Minnesota, and I got a lot of scientific information about how there was a lot more oxygen in the air, and because people can grow large tomatoes and large plants, and animals can be larger. And in fact, the study here, high oxygen levels spawn monster dragonflies. And so I'm going to show you a picture of here's the regular dragonfly, and then I'm going to show you the size estimate of these monster dragonflies that they hypothesized that were larger from 300 million years ago, emulating Earth's oxygen conditions. It must have been much larger. And so here we go. I've done some estimates of these monster dragonflies, and there we go. 15% larger. I was a little disappointed. I was expecting they could pick somebody up and carry them away. I'm not sure that's much bigger. But they were monster back then. And more oxygen in the atmosphere would have supported these huge monstrous creatures. Maybe. But when we do that, when we do these experiments and we think about how much oxygen is there, what most people don't think about is what's the implication to everything else when you change the oxygen levels. So we're going to do that today. We're going to think about the everything else. You would like to think about the monsters, I'm sure. I too. I'm still thinking about this. And some people have hypothesized some really interesting things that could happen, like dinosaurs. They could not live in today's atmosphere, and because of a number of things. So that'll be some future talks, perhaps, how dinosaurs and all that could have survived. But, I mean, come on, monster, that's not that big. So today, though, we're going to think about oxygen, what happens, because to me this is chemical design. What if you have too much or too little, right? Cookies you can mess up if you put too much of something in or too little of something in. And why is there anything different when we talk about air? We can go through the same thing. And when I started to do that, certain things start to reveal themselves and become interesting, at least to me, maybe some chemists, and hopefully to you. So is there evidence of chemical design when it comes to oxygen? Okay, what happens if we change it? 21% of dry air, meaning we're not counting the water, because that changes all the time, and we're going through a lull here in Michigan in terms of water in the air. And you'll know because your hands will dry up, and you'll get cracks and all those things. So I'm going to give you 10 reasons, at least 10, why I think Earth has oxygen, and it's the result of chemical design. And when I say the word design, I am being very specific that some being, and I'm implicating the God of heaven, did this. When you see design, it means can't happen by chance. There's no chance that chance did what we're talking about. Okay? And so when we see design, we're seeing the handiwork of a creator. Now, some people who talk about intelligent design, they are not naming who the creator is. They're just saying a mind had to do that. So I'm taking this a step further and saying, I'm going to look at the chemistry, and I think there is evidence of a mind, and we know who it is. Okay? Reminder, too much, bad. Too little, bad. And if we see a system that has the right amount, that's probably some evidence of chemical design. I'll share some more things like that later on. Okay, a little bit about the oxygen that you breathe. A lot of people just think it's an oxygen atom that's flying around. And we're learning in our class, if you maybe have learned elsewhere, it's actually two oxygen atoms double bonded together. They're really strongly held together. And there we go, O2. So it's actually this little diatomic molecule that's flying around that we need for life. And, turns out, needed for fire. So we're going to kind of focus on those things to begin with. All right? It's nonpolar. It doesn't like to mix with water very well. And we're going to see evidence of that. It's a gas, odorless, colorless, tasteless, but fun oxygen. Okay? It's very reactive. It means you can do a lot of cool chemistry with it, and we're going to do some of that today. Okay, 21% in our air. What happens if you have more? What happens if you have less? The evidence of oxygen and its reactivity is all around us. This is what iron normally looks like if you were to make it and smelt it and do all sorts of manufacturing to get pure iron. And as many of you know, because we've lived in the northern climates, if you just let pure iron stay out for a while, it will look like this. Okay? It combines with oxygen because the oxygen in our air is reactive. In fact, it's dangerous. And you'd say, no, it's not, because it makes me alive. Yeah, because it's causing chemical reactions, but to make many things, and you're going to see, it's dangerous, it's reactive. Okay, everything, or most things that we find on our planet are what we call oxides. They are things that have already reacted with oxygen, because oxygen's very reactive. Silicon dioxide, you may call it sand, okay? But it's an oxide. Calcium carbonate, that's an oxide. That's limestone. So a lot of rocks and sand are just compounds of oxygen because they have reacted with oxygen, or they were created that way, but there's definitely a lot of oxygen there. So oxygen's very reactive, and it can be for very dangerous things. Now I think one of the top reasons why there's design is when I think of the size of Earth relative to its gravity and to the composition of our air. You see, Earth has a certain amount of gravity because of its size. And because of that, it actually holds on to certain molecules, and it lets other ones go. And I have a few examples of these gases here in the back. I didn't want to bring them quite out yet until now. Okay, so I have some balloons here, and this is, okay, that one. No, not that one. Oh, these guys want to fly around on me. Wait, I had them just right in here. Where's the orange one? So I'm going to pull out one of these balloons that likes to fly away. Not that one. Ah, there it is. All right. What balloon is that? Helium, right? And if I, oops, sorry, I was going to hand it around. No. When would it stop? If you were to let this go outside, when would it stop? It would pop, but what about the helium inside? Because that's actually what we're concerned about. The balloon will pop. What happens to the helium? It keeps going. When does it stop? It may not stop. It definitely gets into the outer regions of our atmosphere, and it probably gets blown away by this thing called the solar wind. It leaves. I wonder how long that will stay up. So we'll see if it's still up tomorrow. Okay? So everywhere I go, I leave a helium balloon when we do this talk. All right. Now there is another balloon, gas, all right, that's very similar to that one. And I've written it right here. Hydrogen. H2. So this one is very much like that, and if I were to let it go, I don't want to lose this one. Okay? That has this gas in here, and just like helium, leaves our planet. So hopefully you can see that in the picture. Earth's gravity is not large or strong enough to hold onto these gases. Think of our gravity as a filter. The small, light gases leave, and the heavy gases are held onto the Earth. Okay? That is important, because if it held on to these kind of gases, hydrogen and oxygen and these gases don't always play well with each other. So you came on the right day to see some of these reactions here. Oh man, I'm going to have to move some of this stuff. So we are going to run some chemical reactions here on hydrogen and different gases here, and I brought my clip so we could hold on to them and they won't fly away. Got to give it some weight here. Okay, got to get something that has extra gravity. And we are going to pop these balloons. And maybe some of you have seen this before. I've seen it hundreds of times, and I'm double checking, but it's always fun. And it's a great reminder of why we should not have an atmosphere full of gases like this with oxygen. And so I think I have this here. Oh, there we go. And so we're going to pop the balloons. I'll do the first one, and maybe we can get a volunteer for some of the other ones here. And if you've seen this before, we'll have some fun again. All right, so we're going to light this balloon, okay, with this candle, and we're going to see what happens. Now, there's pure hydrogen in here, but there's some oxygen around this balloon, okay? I forgot to warn my colleagues here, but 3, 2, 1, and 0. Oh, did I tell you that was going to explode? That's going to explode. Wow! Woo! You guys feel it? Yeah, that's cool. See, front row. These are the warm seats. All right. Hydrogen, flammable, and fun. But flammable. That's the main part of that. Okay. Now, let's see. What do we got here? That's another one. Go with oxygen. Now you may have heard oxygen is needed for fires. So I have a balloon of pure oxygen, and we're going to see, can it outdo that hydrogen there? I have a volunteer. Probably a lot of volunteers. Cameron? You want to light it? Jacob? You want to light this balloon? It's oxygen, man. Oh, all right, Zoe, come on. All right. You can come from this side right here. Oh, I have like 2 little secret candles in there. Okay, you hold it there. I'm going to run the other direction. Okay? And just give me a chance to get away. All right. Okay. All right, go ahead. Sneak it right underneath there. 3, 2, 1. Boom! Oh! Well, go ahead and let that out. Thank you. Thank you very much. Give Zoe a hand. That was very dangerous. Woo! Was that exciting? Now, oxygen doesn't burn, you guys. Oxygen helps things to burn. Ooh, let's put the 2 together. Okay? So, I have some balloons with a mix. Okay? And when you put these 2 things together, it changes a little bit. Or quite a bit. Now, do we have a braver soul? Okay. All right, let's do it. Okay. All right, you're gonna. Oh my God! This one will be a little louder, okay?
Oh, jeez.
All right, grab your fire stick here. All right.
Hey, don't get scared. Don't scared. Hey.
I'll give you the signal, okay?
Don't scared. No screams.
All right. This one's gonna be louder. You're gonna need your earplugs.
Oh.
Are you ready? 3, 2, 1. Was that louder? Was that louder? I can't really tell. Was it louder? It was a little louder. Thank you. All right. Woo! Yay, survived. We do this one a lot here, and it's loud enough, and it was loosening these light bulbs up here. And one day, one of them fell on and almost hit me in the shoulder, so I looked up. And they're in there nice. Wow! Hydrogen and oxygen. Is that a fun combination or what? Okay? I have a couple, just extra. Maybe at the end we'll do a couple more. If we have it. So would you like an atmosphere full of hydrogen and oxygen?
No.
No, not really. Not really. So it just so happens that our Earth has the right size, the right gravity to release hydrogen and keep oxygen. You see, when scientists are looking for planets that are large Earths, we've got to be careful. There's a good chance there may not be life on there because you don't want to hold on to hydrogen. Well, you might say, how do you know that planets with large gravity hold on to hydrogen? Well, they often hold on to these really light gases like helium and hydrogen. And just one little helium joke before we go. Okay? Laugh again. See, it made you laugh. All right. Woo! Okay, this is it's a chart of the gases. What I want you to focus in on right now is the gas composition of the gas giants. They are mainly like 80 to 90% hydrogen gas. And then largely helium is the other bit. And it looks like we've got some methane. You will find little to no oxygen on these planets. Man, I wonder where oxygen comes from. I wonder how did our planet get 21%? You see, the only other planet that kind of has a little oxygen is Mercury. Oh man, it's 42%. Well, it's 42% of essentially nothing. There is so little atmosphere and some of it's oxygen. And it may that be a result of the chemical reaction. I mean, it has sodium in its air. Sodium, pure sodium metal. Not like salt, okay? And then some hydrogen and some oxygen. There's so little, it's the percentages betray what's actually going on there. But these large planets can hold on to hydrogen, and they're mainly hydrogen because it's very common. And our planet is constantly making it, but letting it go. Okay? It is too reactive to have as an atmospheric gas. We don't find it on any other planet other than Mercury, but that almost doesn't count. Okay? It's basically just vaporizing some rocks there. Okay? An incredibly low pressure on Mercury. 1 times 10 to the minus 4 atmosphere, 14 atmosphere. So it's about 1 trillion times less. Okay, so these are some numbers that go behind the density. Hydrogen and helium, very light. They leave, whoop, they float away. Okay, and argon, carbon dioxide, and ozone are all very heavy gases. They actually sink down. Okay, and we're going to talk a lot more about ozone, not in this talk, but in another one. There's a lot of design in there as well. Okay, nitrogen, oxygen, the two main gases just so happen to have the same density there in our mixture. That's a good thing. We'll talk more about that later. Let's talk about the health as it relates to the levels of oxygen. Okay, this is between so OSHA. Okay, OSHA, Occupational Health and Safety Administration. They govern a lot of what's good and what's bad for buildings and workspaces and these sort of things. They say 19 and 23%. Okay, and it shouldn't go any more or any less than those numbers. But who's OSHA? Come on. Well, you'll get in trouble if you violate those things. But just even climbing up a mountain, the pressure goes down and sort of the percentage of oxygen goes down. And at 17%, you feel like a college student at the end of the week. Okay? Impaired mental abilities. Okay. Just saying. Okay? And perhaps a professor. Okay? And then less than that, 14%, you can hardly do anything. And less than 10%, you will lose consciousness. We know from practical experience, I mean, I even get to 8,000 feet, and my wife can testify. That's my wife down there, and holding the camera, thank you. At about 8,000 feet altitude, and I don't know what that percentage would be roughly, but man, I wasn't doing very well. What's the highest anyone's gone in terms of altitude? What do you got there, Brenda? Oh, what's that?
It was like 5,000, and then we went to 900.
15? Nice. You got over 15 or 14? Oh, some 15s? Okay. What do you got?
I live at 5,000 and I go to 12.
15 to or 5 to 12.
Yeah.
Wow. Man, I was not doing good around Colorado, which is mile high. Well, 5,283 feet. And anybody over 15? Anybody over 15? Wow, we did go up around 14, I think, in Colorado. Whew, man, that is not. You go any higher? Oh, how high did that go? You know, the Alps, way up there. Oh, nice. Okay. All right. So, how did you guys feel? Some people get used to it. Man, I get cranky. He's like, why he's cranky now? I wonder what he's like at 8,000 feet. You know. Whew. So less oxygen, life does not do well, at least large life. Large animal creatures like us do not do well. And so too low, we already know there's a problem if you go too low. But how low? And it doesn't take very much lower for us to start struggling in a big way. What about high levels? Well, apparently it leads to large creatures, and it should be great for you. Places like the Mayo Clinic, man, we were just there, talk about and have instruments for hyperbaric oxygen. This actually seems really intriguing. It looks like when you can pressurize your whole body, you can push some oxygen in there, in your tissues, it leads to some rapid healing. And so these things are becoming more and more popular for treating all sorts of diseases and things. And they just put a couple of atmospheres of oxygen in there and for a short period of time. Now here are some of the potential risks. The high pressure could lead to temporary nearsightedness. Okay, but college can lead to long-term nearsightedness. And I can see on your faces. Okay, but this can cause it. Middle ear injuries, that's more to the pressure. Lung collapse, once again pressure. The last one, seizures, oxygen toxicity in your central nervous system. That seems to be a problem, and it is. You can be exposed to high levels of oxygen only for short periods of time. I have a few friends, or a friend, or a colleague, or someone I know is starting these businesses to go around and have hyperbaric oxygen chambers. And recently they put Mark Finley through some to help some disease or sickness that he has. And he had to do 28 treatments because you can't just go in there once. It's a little by little. And it did help him. And I've actually been thinking about my mother, Savannah's grandmother here. She was not doing very well, and I think this would actually help her. Unfortunately, she cannot travel in a car to get there, so that's not good. But hyperbaric, hyper means a lot, baric means pressure, so high pressure oxygen looks like it could heal a lot of things. But you cannot do it for a long time because it's toxic. And this is the side that a lot of people don't think about. Oh yeah, more oxygen, bigger dragonflies, larger, dinosaurs, and everything's huge. Tomatoes are huge. Yeah, but it's not. What does it do to people? What does it do to life for long periods of time? There are limits to how much you can be exposed to. Okay, and divers know about this because they deal with breathing all sorts of gases. And diving cylinders typically for breathing air have oxygen-enriched air mixes. They rarely contain pure oxygen except for when used for rebreathing and diving, shallow decompression stops. So they know that it can lead to oxygen toxicity, a highly dangerous condition that can trigger seizures and lead to drowning. You start to get really loopy, can't make good decisions, and that's from too much oxygen. Are you starting to see some design elements? Too little, obviously we know is bad, but too much is bad. We often don't think about that. More oxygen. Oxygen's great. It keeps us alive. Yeah, at the level that we have. Okay? So too much oxygen can be very, very dangerous. Now, I just got this text from my mom's doctor here recently. In fact, you can see the date, 10/31. I've been asking for her to have more oxygen because oxygen apparently is awesome. And they gave me a great statement of how design is very important. Oxygen isn't really something we should prescribe without understanding what's going on. Too much oxygen can diminish the brain's drive to breathe, and so we only use it in cases of significant oxygen deprivation. My mom's name's Helen. We can make Helen an appointment to check to see if there's anything that would indicate she should do that. Your body is great at extracting the oxygen that's there, and so they gave me a great design argument right there. Too much can actually start to change how your body works with the oxygen and that we have right now. Okay, so they're very concerned. So too much is bad. You can't just. So I'm hoping for anything. We're desperate to help my mother feel better. She's in a lot of pain and not doing very good. Okay, so where do we put those levels? So certainly below 17 is not good. Higher than 40 is kind of what I get from some of those things. in terms of oxygen toxicity. Man, why didn't I put more oxygen? Is he trying to keep the helium from us? What's going on? Okay, so thankfully God doesn't just think about living systems, he thinks about the chemistry of our planet, and we need to think about fires. This is the next thing that needs oxygen. And so I thought I would do a little demonstration with fires here. And you see, for many years and decades and centuries, they thought that fire was the result of a substance called phlogiston. So this is kind of fun. You can do this kind of thing at home. And scientists like Antoine Lavoisier and Priestley, they did some experiments to show that the air actually is composed of something called oxygen, which we take for granted now. But they used to think that when there was a fire and that you would close off the fire in a chamber like this, the reason why it would go out is that the chamber would fill up with a substance called phlogiston, and once the container was full, it would go out. So the phlogiston theory, you guys heard of that? Doesn't really work anymore because oxygen is not a thing. Or I mean, phlogiston's not a thing because oxygen's our thing that we realize is there. You guys see what's happening to the water level in there? Or were you looking at the candle? Okay? I don't know if I can do it again. So by consuming, that fire consumes the oxygen, it lowered the pressure inside. The air pressure pushes the water that was in here inside of this container. Hopefully you can see that. And now if I lift it up, I got my candle all wet, so it's hard to do again. And there's very little oxygen in here. If I run it again, I have to actually fill it back up, and it won't work very well. So this is fun to do at home, very safe, and we can recognize some of the properties of oxygen, and that it takes up about 20% of our air. Sometimes you can, it's pretty close to that volume calculation there. I don't need that. Okay? And so what's the deal with oxygen and fire? Well, we definitely need it. We need a fuel source. You need oxygen. You need a spark to get it going. And phlogiston's not there anymore. That was a bad idea. So a lot of us in our class use Bunsen burners. And in the interest of time, I think I'm just going to skip over the video training here. But we recognize that as you turn the Bunsen burner and get that going, that the flame actually gets hotter. So I'm going to skip over that. So when you add more oxygen into a fire, it gets hotter. Oxygen and the temperature of a fire are directly related to each other. So this is what's called the cool flame. When you just add fuel and very little oxygen, 300 degrees Celsius, there's nothing cold about that flame. It will melt you. Okay. But as you increase the oxygen level, you can get these really cool double flame here, and it is super hot. You can melt a lot of things there, and it gets up over 1,000 degrees Celsius. Okay. Now in the lab, we get about 700 to 800 degrees, which is really hot. Okay. So more oxygen, hotter fires. And so when in the story of Nebuchadnezzar and Shadrach, Meshach, and Abednego. Oh, my mom's calling. She knows I was talking about her. All right. Yeah. Sorry, Mom. We're trying to help. Okay. So Shadrach, Meshach, and Abednego, we know the story. They didn't bow down to the idol, and they got thrown in the fire because Nebuchadnezzar was so mad. You didn't bow down to my idol. And he said, make that fire 7 times hotter. And it was fun to look at the Bible commentaries because they threw more wood on the fire, or they put more coal in it. No, they didn't. No, they didn't. They probably had big bellows in there. These big ones. You can get these like $9 or $10 at Home Depot. I didn't know they still sold these things. All right. And they probably like, let's get some more oxygen in there. Well, or whatever the Babylonian word was for that. I'm not really sure. Okay. And so they knew they needed to get a lot more oxygen in there. Oh, I need to turn my phone down from before. All right. So they were getting a lot of oxygen into the fire to make it hotter, and it was so hot we know that the soldiers died getting these 3 guys in there. Oh, and we know that there was a 4th one that Jesus showed up there with them. What happens to having more oxygen in fires? They're hotter. They burn things faster. They are very dangerous with more oxygen. People know this, but we just don't put it all together. Okay, this is from some fire websites and from OSHA. In an oxygen-enriched atmospheres, areas where there's medical oxygen, the underlying combustion is greatly accelerated. Materials that resist burning in air can burn vigorously when there's extra oxygen around. This is the problem with oxygen. If there's even a little bit more, things will start burning that would never be able to burn before. OSHA sets the safe level to about 2% more than what we have in our atmosphere. I like to talk to firefighters, and I'm like, oh, what level would you set it at? Do you like to have any more oxygen? They're like, no more oxygen. Fires are already hard enough to fight. Let's not have any more oxygen at all. Okay? So, too little oxygen, things don't burn just like we don't live. But too much oxygen, fires are greatly more challenging to burn up, to put out. Man, imagine the forest fires we would have if we had more oxygen in our air. So now, when I think about those levels, those comments, and looking at this information, perhaps that level is a little bit more, 23, 24% oxygen is a safe level. And even given a really wide range, 25 to 17%, those are some really wide numbers. I think the level's even tighter than that. We are sitting right in a perfect level for life and for fires. Okay? So 21% is ideal for all of these things to happen. And that's amazing. And a lot of people recognize that when yeah, that's right. We should think about fires. Well, God thought about fires. He also thought about fish. You see, the oxygen in the air is the exact same oxygen that creatures in the ocean need to breathe. Now, this is a great question that I love to ask a general audience. Where does the oxygen come from that fish need? And I've had a number of people go, oh, it's H2O, silly. And it's the O in the water, that H2O, right? Oh, oxygen. That's what they breathe. And it couldn't be farther from the truth. That oxygen is the exact same oxygen molecule that they use, that we use. They're a lot more efficient with it, and they can live. And one way to show how that works is this methylene blue experiment. You see, there is a blue compound in there that, when it mixes with oxygen that's sitting up top here, and if I can mix that oxygen down into that liquid, this thing will turn blue. And all I need to do is mix it with oxygen, and it will turn blue. Okay? So methylene blue with oxygen is blue. I have another chemical reaction in here that is consuming the oxygen, the O2, in the liquid here. And as that consumes it, the oxygen in the liquid goes away, and this will return back to its clear color. And that's not a very fast reaction, so we'll just keep our eye on it while we're doing this. So the oxygen in the air is pushed down into the liquid. And this is given a name for this relationship here that I'll tell you enough. So if you're going to design water, you got to think about how much oxygen is pushed into the water to make sure those levels are okay. So, okay, methylene blue, colorless, without oxygen, and it's blue with oxygen, and it's still blue there. Okay? And so I can keep mixing it with the oxygen above there. So fish just have an awesome design to extract the O2 out of the water. It's not the O, it's the O2. All right? They're awesome. Lots of surface area, and they can capture the oxygen. They can live on a lower level because they have a different design. Okay? This property of pushing the oxygen into the liquid is called Henry's Law, and my general chemistry students are going to probably learn that tomorrow or Thursday. Okay, I think tomorrow. And so this is a very important law. It's right there with all these other laws of Boyle's, Charles, and the ideal gas law. And if the greater the pressure on top, the more gas you'll have in the liquid. So Henry's law is about how much pressure of gas is on top to how much oxygen is in there. Okay? So we can go through the calculations, and we will in class, but we're not going to do it here. All right? And so each gas, nitrogen, oxygen, and carbon dioxide, have their own Henry's law relationship to the pressure on top, to the liquid, to the levels of those gases in the water. It's as if somebody thought about all of that, so there would be low levels for the fish to have, and not too much of each one. You see, that level that's in the oceans are finely tuned for that life to exist. Too much can lead to what's called gas bubble disease, or the bends. It's something that humans get when we get too much oxygen or nitrogen in our in our system, and then too little, of course, they will die. So same thing to us. So these levels are really finely tuned to have life in the oceans. So someone had to think about that. One example of this design is how easy it is to get rid of that oxygen and to have huge fish kills. And this is a picture of a huge fish kill that took place in 2011, another one in 2011, in 2009, and they're all over the place. That's a fish kill, that's not a dirt road. Okay? And so look at all those dead fish. And boy, I think we got a video here of one. Man, you can just type in fish kills. They're just like very common. There's another fish kill. And what happens is there's just something that, oh, we got one guy's alive. Something is taking away the oxygen and destroying the balance in there, and then the fish die because they run out of oxygen. And it's fun to hear the professionals talk about this. I have one, I think on the next one. Man, they're just dead. This sometimes happens in Lake Michigan. It's not. All right. Yeah, of course. All right, there's a bunch of dead fish. All right, we're going to go on to the next one. All right, so this was another one that took place down in Louisiana.
Thousands of fish are dead at the mouth of a shipping channel, as well as a dead whale that was reported in Venice today. The species include crabs, stingrays, eel, drum, speckled trouts, and redfish. The video you're about to see is not a gravel road. Those are the dead fish. Plaquemines Parish President Billy Manchester sent these pictures. He says that there is no testing going on to determine if the fish are dead from the oil spill, although the northern Gulf has suffered a persistent dead zone of low oxygen, blamed on nutrient-rich runoff from the Mississippi River. Nungesser says that this is different because usually the kills happen to only one or two species of fish.
We're talking about the long-term testing of the quality of the water, the fish, and the environment. And we don't see a collective group really wanting to know what's going on, and we need to demand that happens.
What do you make of this fish kill that happened in Plaquemines Parish over the weekend?
There was some redfish that died in this particular case. Not a whole lot of them. They were kind of scattered, which again indicates probably an oxygenation problem. One dolphin in it, but that could be natural mortality. I mean, those are lung-breathing animals. They don't breathe by gills, so a low oxygen problem in the water would not affect the dolphin. There is another possibility that the microbes and the bacteria that have been eating some of this oil, maybe that caused the oxygenation problem.
No big deal. It just happens. Well, it's because it's so finely tuned, it doesn't take much for it to change. It's called eutrophication, when you get too much nutrient-rich runoff from farms. If farmers are not adding the right amount or too much fertilizers, a lot of that runs in the water. There's a bloom in plant life, and then they run out of nutrients, then they die, then the bacteria take over. As the bacteria take over, they consume a lot of the oxygen, and levels drop a little bit, and fish die. Complicated, but we know what's happening, and so farmers need to really balance how they put their nutrients on their fields, or we get these dead zones. In fact, this is Louisiana, near the mouth here of the Mississippi River, and there's a dead zone around there because there's very little oxygen because of that nutrient-rich runoff. Okay, so whoever thought about oxygen in the air thought about pushing enough into the water so that life can exist, but it's all of that's finely tuned. And then because of the fish kills can help demonstrate that. And lots of fish kills. All right. Man, I said there was 10 things. We're going to go quick on these last ones. I find this amazing right here. This is fun. You guys should try this at home sometime. The oxygen levels work really well with water. What I've done in this little picture, I'm going to show you a video, is I have hot water that I had as yellow, and I took cold water as blue. I would do it in front of you, but it takes too long. And I mixed them. And in this one, I started with a certain one on the bottom. I guess the yellow one. And this one, I started with the blue cold one on the bottom. And you can keep them separated because their densities are different. So cold water and hot water have different densities. And I think I have a video. Cold water is more dense, so it sinks, and the hot one's less dense. I think I have a video here. All right. So I do it really fast. Okay? Put in the cold, and then if you're careful, you can put the hot on top, and it will stay on top. And you can tell because the colors aren't mixing. Okay? Now, cold water holds on to more oxygen. All right. And then after an hour or so, they still stay separated. I think I did it. Okay, now if you put hot water first on the bottom, here's what happens. Okay, so there's the hot water. Now, if you put the dense, heavy, cold water on top, it just sinks down through. And you don't get the separation anymore. It just mixes. Okay? That shows how the cold water is more dense. Yeah, that's fun. All right. So what does that have to do with anything? Well, cold water holds on to more oxygen. This is part of Henry's law. And as that cold water sinks down, it takes oxygen to the lower levels of the oceans and then the lakes. And that provides the oxygen that's needed for life at all levels within the ocean. In fact, this creates currents and movement in the oceans. And this is a graph that sort of tells you how much oxygen is in different parts of the ocean. The colder it is, the darker, the redder the colors, the more oxygen. So it's actually really good for fish and life in the oceans in cold water. They actually have more oxygen. We like the warm water. That's because we don't have to breathe the oxygen in it. We can just sit in the warmth. Turns out along the equator, there's pretty low oxygen levels in the water. So what's happening, now this is a side view of the ocean. Antarctica, Greenland, this is the depth here. And so in these cold polar areas, it collects oxygen and takes it down low. And as it gets near the equator, it warms up and comes back up. And it creates what's called the Great Conveyor Belt. And it's basically delivering oxygen down low for all these creatures, and it stirs the ocean. And all of this happens because it's all automated in some ways, chemically. It's amazing. And that oxygen brings life to the ocean floors, but it also provides a reactive chemical to kill a lot of the stuff that's coming out from the center of the earth. There's a lot of sulfur and stuff that comes out of these black smokers, and the oxygen reacts with that, neutralizing it so it's not toxic for life in the oceans. So there's a lot of great things that are happening that we don't even know about. Reason 6, oxygen is one of the molecules that provides a lot more power. I've been reading books about oxygen when people think about it, and they're like, there's no other really good reaction to provide power for life. So I call it lots of power there. Okay? We know that from our last experiment that there's friction with the air and meteors coming in, and that oxygen helps to accelerate those burning and the fire that comes in. There's over 100 tons every day of meteors hitting us. This is why your room is dusty, okay? You can blame the meteors and the asteroids coming through the atmosphere, and they're just sprinkling dust all over. This is what my wife complains about. Where does this dust come from? It's coming from the meteors. It's not from me, I can assure you, okay? And why is my room so dusty? This is why you got to keep dusting. There is 100 tons of meteor fragments and dust falling every day just because of all this stuff. And we know nothing about it because it's all happening without us knowing. Okay. Another reason why oxygen is so finely tuned is because it's part of a recycling system. We know that plants make oxygen as they consume carbon dioxide. This is the great carbon-oxygen cycle that we have between plants and animals. And anytime you see a cycle, I actually think this is a great evidence of chemical design, because you got to have both parties in place at roughly the same time, or they will not be able to develop independently of each other. Now, plants can do a little bit by themselves, but animals cannot live without plant life. Imagine if you were to create animals first, without plants. We just assume they all kind of come together. It's because that's what we experience every day. Okay? So anytime you see chemical cycles, I think this is evidence of design, because you got to have both things happening, or more things happening at the same time. Now, the carbon dioxide cycle here, I like to think about the creation week if we started with animals on like day 3, and then we brought in the plants on day 6. How long could animals live without the oxygen from plant and plant life? Okay? Not that long. Okay? So that wouldn't work. The other thing is, and this is a whole other talk, and I'm just going to say one sentence about planets, not plants, planets without life cannot support high levels of oxygen. Research indicates that Earth's oxygen-rich atmosphere is a result of living systems. Plants are the ways to create oxygen, oxygenated atmospheres. We know of no other way that is a good way to produce lots of oxygen into an atmosphere. You've got to have life first. This, I think, speaks largely to the design of our planet. You got to have life first in order to have oxygen, because that's what makes life, oxygen. Thankfully, oxygen is not a greenhouse gas. Our greenhouse gas is carbon dioxide and water. And if it was a greenhouse gas, we would burn up because it would hold on to too much heat. Ozone comes from oxygen. Lightning and energy, UV light, hits oxygen, breaks apart, makes ozone. So, and we know ozone protects us from other UV lights. So that ozone comes from oxygen. So we want to thank oxygen for our ozone. All right? And this is where I'm going to wrap it up. So there is a lot to this, and I could keep going, but we're not going to. So let's think about all these different things real quick. Just so happens that Earth's gravity holds on to oxygen, but lets hydrogen go. Okay? Oxygen levels are pretty much safe at most places on land, except for Mount Everest. Right? And some places that are a little higher. We have enough oxygen for safe fires. They don't really get out of control too often, but we know that they do sometimes. Oxygen solubility in water allows for life in water. Cold water holds more oxygen that sinks, bringing oxygen everywhere else. We have a great recycling system in plants for that, and we know oxygen's great for respiration. Oxygen protects us from sun's the space debris and creates ozone. Ozone is mainly in the upper atmosphere, but it's very dense. I wonder how that stays up there. And it's not a greenhouse gas. And I see a whole system working together that somebody thought about that's all designed together. We see gears, we go, somebody put that together. We see chemistry, and we go, too hard. It all happens by chance. Not a chance. Someone has been working behind the scenes. Thank you for coming today. And if you have your sheet, you can bring it down. Thank you for coming. No, you got it.